Okay, guys, so we're going to do a video on chapter 17, which is the beginning of our sampling distribution models. We have 4 videos for this. This is the first one. So to begin, I want to start talking about what we know about sampling. So this is just a quick recap on what you probably already know. The process of statistical inference comes from using information from a sample to draw conclusions about a wider population. So very often it is nearly impossible to reach an entire population. So we have to rely on samples to draw conclusions from. So that may be something like if you are looking to see how much gasoline prices vary in a large city. To find out, you would find the price per gallon of regular gasoline at a random sample of 10 gas stations in the city on the same day. You're not going to look for every single gas station in that city. So you could look at kind of the diagram there to see how it would work. So in a population, you have a small sample. From that, you collect data. You make an inference from the data you collected from your sample to make a conclusion about your population. Okay, so a sampling distribution. So different random samples give different values for a statistic. The distribution of the statistics over all possible samples is called the sampling distribution. The sampling distribution model shows a behavior or shows the behavior of the statistics over all the possible samples for the same size n. Because we can never see all possible samples, we can often use a model as a practical way of describing the theoretical sample distribution. Okay, so here's kind of a little bit of an example that we were going to do in class, but it turned into a video. So let me set up a background. So there's a population of about 200 colored chips, not of definitely 200 colored chips, with 100 having the same color, let's say red. The parameter, which is referring to your population, is the actual proportion of red chips in the population. A statistics class took repeated samples of size 20 from the population and recorded the individual proportions of red chips on the dot plot below. Okay, so I want us to realize first that this dot plot is showing they're repeated samples of size 20. So this is a dot plot of different samples being taken from that population of 200. So they pulled out 20, they counted their red, they put it back in, the next student came, took out their 20, counted the red. Every time the new student came up, they plotted on the dot plot, okay? So let's see what we know about the graph. So we can see that it's roughly symmetric. We have about a single peak. It looks close to 0.5. Okay, the mean here, I'm just going to tell you, is 0.499. Okay, so our balance point. Our spread here, or standard deviation, I'm just going to tell you, is 0.112. There are clearly no outliers, or at least it doesn't appear to be. So what we want to consider here, guys, is that this is only 35 different simple random samples of 20 chips. There are many, many simple random samples of size 20 for a population of 200. It is usually entirely too difficult to do this, so we simulate the process of taking many, many samples and create an approximate sampling distribution. Okay. So strictly speaking, the sampling distribution is the ideal pattern that would emerge if we looked at all possible samples of size 20 from our population of chips. In our stats class, we simulated a smaller number of samples, though, in order to approximate our sampling distribution. It's not impossible. It would just take you way, way too long and not worth taking all the samples that can be made of the 200 chips. So, certain software, though, will do it much easier than we can, or much faster than we can by hand, okay? So we use software to simulate using 500 simple random samples of size 20, so far beyond the 35 of that stats class. Still 100 red, 100 blue in the population. Okay, below here's the dot plot of the values of the sample proportions of red chips from these 500 samples. So here's your dot plot, but now it's 500 as opposed to 35. So if we were to describe this distribution, we see a lot of the same that we saw in just the 35 simple random samples. Okay, so we have a symmetric shape. It's unimodal. The center around 0.5 again. Okay, the spread, we are obviously, I'm not going to get you an exact number on this one, but we could say that it's mostly between 0.25 and 0.75, which is about the same as the last one. Maybe it's a little off, but not by much. No, it looks like in this one we might have an outlier at 0.15, okay? So you could see that even though it's much, much more than 35 samples, okay, it's about the same approximation for your sampling distribution. So just a few questions that we can answer about this quickly. So would it be surprising to get a sample proportion of 0.85 or higher in an SRS of size 20 when your proportion would be 0.5, okay? It would be very unlikely to obtain an SRS of 20 chips in which your proportion would be 0.85. If your population here is only 0.5, a value as large as 0.85, it's probably, it never occurred in 500 samples, so it's very unlikely to occur, okay? If it didn't happen in 500, it's probably not going to happen. So suppose your teacher prepares a bag with 200 chips and claims that half of them are red. A classmate takes an SRS of 200 chips, 17 of them are red. What would you conclude? So if 17 are red, then your proportion 17 out of 20, that's your 0.85. Okay, so the student's result gives strong evidence against the teacher's claim. As noted above, it is very unlikely to get a sample proportion of 0.85 or higher if your population proportion is 0.5. So if you ended up with 17 out of 20, more than likely your teacher's claim about the proportion being 0.5 is incorrect, or she's lying to you. So, okay, so let's talk a little bit more about sampling distributions and some variations between each sample, okay? So the following is showing taking many simple random samples of size 20 and creating a sampling distribution from it. So still kind of working with that chip problem, okay? You have 200, here's your population. Here's your population distribution, okay? 100 red, 100 blue, okay? One simple random sample produced 8 out of 20, where another one produced 11 out of 20 red, and the other one produced 13 out of 20, okay? So as you can see, your proportion will vary from sample to sample. The value of a statistic varies in repeated random sampling. Okay, so this we can refer to as our sampling variability. So there is a variability that we expect to see from one sample, from one random sample to another. It is sometimes called